Let's take a look at how we can model a situation with logarithms. So we're going to use this one of the population of San Diego starting in 1980, and then knowing about the 2000 population, and we're going to find what was it in 2018. Suppose I should say what was the population in 2018, okay? And then when will the population reach 2 million people? Well, let's figure that out. We're going to use the formula. Let's see, well, I'll put that here for A. So let's draw this here. As we start doing A, we're going to use this formula. A equals A with a sub-zero, E raised to the KT. So this A is the amount at a certain time frame at T. And of course, then that's time. This one, A0, is the initial amount. And the K is a constant. It's a constant that's just for this situation. So the first thing we need to do is solve for K. First, solve for K, because the other information we will get from what's given to us. Well, actually, let's take a look at that. So one of the things this tells us here is that the time was 1980, and the population in that year was 875,000. And that's the A. However, what I'm going to do here is I'm going to take away the 1980, because this is actually the initial starting year. This is the start of this problem. Not when San Diego started, of course, but it is the start of the problem. So it's actually the 0th year, and then it grows from that year, or our modeling of it. And then what we have here is another TA, 2000, which is 20 years later. And the amount then was 1144000. Okay, now one of the things we're going to do here is to write it, to make it much easier to do, we're going to take away the zeros here. So that means our two equations, or our 2 points that we have, is 0,875 and 20,1144. And so those are the ones that we're going to use with T and A. The first one gives us the initial. So actually what we're going to do is we're going to fill in each of these things. And E, of course, is just on the calculator. And because we're going to fill in the others, K will be the only thing we don't know, and that's what we're going to do. So the first thing we're doing here is we're solving for K. So using 0 and 875 and 20, 1 or 1144. I'll do it that way. We put too many commas in there. So we're going to do the initial amount. In fact, let me write this out again first, and right underneath it, we'll put the numbers for it. So the initial amount, oh, no, not the initial. The initial amount will go here, 875. We don't know what K is, but we know that the time is 0. Oh, no, the time is 20 with the amount of 1144. So notice that this is filled in, this is filled in, this is filled in, and the E is on the calculator. So the only thing we need to do is to solve for K. So the first thing we'll do is divide by the 875, divide by 875 on both sides, and that gives us 1.3074, and I'll put an approximation there, E to the 20K. So this is where we use log or natural log. Because it has an e in it, we use natural log. Log 1.3074 is approximately natural log of e to the 20k. And what happens here is then that this cancels out. So let's write it again. Natural log of 1.3074 is approximately 20k. So let's divide by 20. What I should put over here is apply log both sides, and divide by 2 both sides. So over here we have just k left. So k is going to be approximately the natural log of 1.3074 divided by 2. And what that number means, k is approximately 0.0134. That constant, that's the growth. In fact, if we change that into a percent, we would have 1.34%, and that's the growth of the population is about 1.34%. But we don't need that for our purposes right now. We need it in decimal form. Be careful about something. Be careful. Too easy to forget a zero and write 0.134, which would be wrong. So remember, zeros are significant. So we actually have to use them. Even if they're just placeholders, that actually still makes them very important. So this number, that's our k. What we're going to do now is we're going to go back up here. And I'm going to draw a line down the middle for what we're going to do. Okay, so that was A. Now A is, well, that's to help us get A. A continued. What we now have is that the amount at a certain time, after a certain time, is the initial amount times e to the 0.0134 t. So now if I know a t, I can put it in here. Oh, and I know the initial amount, so I actually should have erased that here. I know the initial amount is 875. So as long as I put in an amount of time, I can then come back and get the amount that goes with it. Okay, and so that's what I'm going to do now. We're going to use, in this one, for 2018, that's 38 years later. I'll write that so it's easier to see the letters. So that means we're going to use the number 38. So t equals 38. So we're going to say that A is 875E 0.013438. And what you do is you put that into the calculator. So you're going to do 875 times E raised to power, put that into parentheses, extra parentheses to keep it only as the power of E. And you're going to get now, A is approximately 1455964, and you get a decimal in here, but because of the thousands that we took out before, because we now have to put them back in, which just means move the decimal 3 different places. And that many people in 2018. There we are. Okay. Now let's take a look at B. So for B, when will the population reach 2 million? Well, in this case, what we have is we don't know the time, but we know that the amount is 2 million. So that means in the equation, when we have the equation, this one we don't know, but we do know this one. So I'm going to write it down here again. I'm going to do B. The amount equals 875 E to the 0.0134 T. And we know we want it to be for 2 million. Again, since we took the thousands out from there, we'll have to do it without the thousands. So instead of 2 million, it's 2,000 is equal to 875 E to the 0.0134 T. And T is the only thing we don't know here, so we can now solve for T. So that means I'm going to divide by that 875. 875, and this time we get the number of approximately 2.2857 e to the 0.013 T. And now we're going to apply natural log to both of them. So we're going to do natural log 2.28. In fact, I think I'll do that back in black and just keep the natural log part in red. 2857 is approximately natural log e to 0.0134. And these will cancel out. So now we have the natural log of 2.2857 is approximately 0.0134 T. So we divide by 0.0134. Divide by 0.0134. And that means that these cancel here. And so we get T is approximately, once you put that into the calculator, divide it, 61.69. So when you figure out, notice it says here, when will it? I suppose we could say after a certain number of years. We could say at almost 62 years later, or we could figure out the actual year. Okay, so if we do the actual year, so we're going to say about 62 years later. But that's not so good because 62 years later than what? Later than 1980? Why choose 1980? What we should is just make it the year itself. So sometime during 2041, the population will reach 2 million. Well, now that's a lot of years, not so far away anymore. Unless the population rate or percentage increases and we get more people coming in, or something happens, we get less people. Okay, so the real answer here is 2041. Let's take a look at another example of doing this kind of thing. There's Phoenix's population. So having done the last one, if you're watching this, why don't you pause and go and do it yourself and figure out if you can do the same things that I did in order to get that. So go ahead, go now, and when you come back, I will start doing it. Welcome back. Let's go ahead and do the different parts of it, just like I did in the last problem. So I'm going to recognize that that'll be the 0 year and the amount. The population was 790. I'm going to take away the zeros for it. And the 2000 population is 20 years, and it's 1327. So I'm going to rewrite a couple of these numbers to make them clearer. So we have those points to work with. So let's figure out here what the K is. Okay, here's the initial amount, 790. And I'm going to use this A and this T. So 1327 equals 790, and it's going to be 20 for the number of years times the K. Oops, I forgot the E. Let's go back there. That's not going to be helpful. It has to be E 2 raised to the power of 20K. So we still want to find the K here. That means our first thing is divide by the 790. And so we get out 6797, approximately E is 20K. And we'll apply natural log to both of these. And then this one will cancel there. We have the natural log of 1.6797, approximately 20K. We divide by 20. And so the constant K is approximately 0.0259. All right, so having done that one, let's see, do I have enough? Yeah, we have a good deal of space down here. So now I'm going to use A equals 790, E raised to the power 0.0259, 0259 times T. And that's what we are looking for next, is that the population of 2018 is 38 years after the 0th year. So we're going to put the 38 in here and we'll figure it out. So when you do that, you get, if you multiply all this out, you get lots of decimals. You multiply this stuff first, or you do 790 times E and then raise that to the power. And A is approximately 2113, and I will put the points here now, 779688. Remember the zeros I didn't count at the beginning, but now they have to go back in, which means move the decimal 3 times. So the population is actually more like 2113779.68.7, but recognize that we can't have a partial person, so we have to round that up. You can't have them only a part. You have to have full people, either round down or round up. So that means approximately 2,113,779. And then 779. What was I here on my bookend? Oh yeah, people. And 20. Is it that 2018? Yep, in 2018. Okay. Now that means we need to change something. I've forgotten that they already had 20 million people or 2 million people by 2018. So that should be 3 million people. So if you did this before, then you would go back and change it to 3 million and see if you're going to get what I'm going to get here. So this was all A. This was the answer to A for the problem. So A was at 2018. Now let's see for 3 million people what it would be. I'm going to do part B. And we're going to use the formula. A equals 790. Formula that's specifically just for this problem, because we had to use a sample amount in the year 2000, what the population was then, to get us this K that is just for this problem. So now what we're going to do is for 3 million people, 3 million is 30000. Let's see, do I have enough zeros? Now I have enough zeros. But we're not going to use those, so it's going to be for 3,000 that we put here. 790E 0.025. And so we'll divide by that 790. And so we'll do 3,000 over 790 on both, or divide by 790 on both sides. Get the number 3.7975, approximately e to the 0.0259t. Now we'll apply the natural log on both sides, because that will enable that to go away. So we have natural log of 3.7975, approximately 0.0259t, and then divide by this one, 0.0259. So t is approximately 51.52. So what we have to do is go from the year 1980 plus 51 years, 51 and about a half years. That's going to be 2031. So 3 million people, and that's about half year. After 51 and a half years, but I don't like that answer. During 2031. That's a much better answer to include 2031. And so I'm going to yellow this to highlight it. I'm going to highlight it. So I'm going to use the green one to highlight that it's 2031. And we'll do that with this one too. Go back up here. Do the same thing with the 2041 here. And the number of people for the problem before. San Diego and then Phoenix. Phoenix is growing a good deal faster. Notice if I look at this percentage over here, that would be about 2.59%, which is actually a good deal more than the 1.34 for San Diego. Let's look at another type of problem. And this one in particular is Newton's law of cooling. So it's a temperature goes down based on the room temperature and the time and all that. So let's actually look this out. Okay. So there's too many t's here in a way. Notice that there's a t here, there's a t here, and a t0 here. So it does say that T is the temperature of the item at the time, T. So that means we have a lowercase t and a capital T. And the lowercase t is the amount of time, and the capital T is the temperature at that time. Okay? So we're going to use that for us. TO is the initial temperature. So here we have a problem with some information. Pizza removed from the oven has a temperature of 450 degrees. And it's sitting in a room that has a temperature of 72 degrees. That, by the way, is the C, the room temperature. After 5 minutes, the temperature of the pizza is down there. So we have an initial amount. So that 72 is the initial. Oh, no, that's not what I want to say. That's the room temperature. The initial amount, or the initial temperature, is 450. And then we have that after 5 minutes, it's at 300. So we can use Newton's law of cooling, which is this formula here, to find a model for the temperature of this pizza. And because of the room temperature, it has a certain exponential amount that it goes down. Okay, going lower instead of higher this time. So let's look at A. So this out here. I'm going to put the formula T equals the room temperature plus the initial temperature minus the room temperature times E raised to the KT. So we know some of that information, right? So let's put in what we have to work out here for part of it. So I should know these three right off the bat. That means that the temperature is equal to the room temperature, 72, plus the initial temperature, 450, minus the 72, raised to EKT. Now, let's say, we have given to us the temperature, or the time with a temperature of 5 minutes and 300. And that's going to help us get the K because we're going to put those in there. We're going to say 300 is equal to 72 plus 450 minus 72 e to the 5 times K. And so that T is there. So I'm going to subtract 72 first on both sides. And if we do that, we get 228 equals, and we have to add these two numbers together. That's 378 e to the 5K. And then we're going to divide 228 by the 378, and we keep working to isolate the K. And that's the number 0.60 317, so I'll make that 2, equals e to the 5K. I'm going to apply natural log to both of these so that these cancel, this cancels out. Natural log of 0.6032 is equal to 5K. Divide by that 5 immediately. And so the K is approximately, so these should all be approximates here. K is approximately negative 0.1011. And now that's an important point, the fact that this is negative, that means it's going down. It's going to bring us down, and at a 10% at a time. And so if I move the decimal over, it would give us 10%, 10.11%. Good enough for what we need here now. So now let's actually figure out with A. We have the formula T equals 72 plus 378 times E. Notice I just did this as the 378 without having to do it separately. And K negative 0.1011 T. So now all we need is an amount of time. And so the first question A is, actually A was to find the model. So A is the model. Good, done. That's the model. B now is to find it with 10 minutes. So let's do that. T is equal to 72 plus 378E negative 0.1011 times 10. So put that into the calculator. Remember to do the multiplying first and then the exponent to that. Oh, wait a minute. Let me rephrase that. Do the exponent of this first. Look that out. And then you're going to multiply it and then you're going to add it. And so it's like step 1, step 2, step 3. So follow the order of operations carefully here. And what happens is you get a temperature of approximately 210 degrees after 10 minutes. Or at 10 minutes might be better. Say at, no, it says after on the problem, after 10 minutes. So okay. So now we know this one. So we have done the model. We have done the after 10 minutes. Now, when will it be 140 minutes? And for that, I'll use some space over here. Okay, I guess I'm going to highlighter separated here. So now what we know, we don't know the time, we know the temperature of 140 degrees. So in that case, we can use the same formula. formula here. But now we're going to fill in the t, the capital T, not the lowercase t. So for part C, t is equal to 72 plus 378 e negative 0.1011 t. This one we already know, so we're going to use 140 degrees equals 72 plus 378 e negative 0.1011 t. So I'm going to divide by the 72 now. Oh, no, not divide, subtract. Let's subtract 72. So I get 68 equals 378 negative 0.1011 t. Now is where I'm going to divide. I'm going to divide by the 378, so that goes away and we can isolate t. 78. And now I'm going to apply natural log to both of these. So on this, actually, let's rewrite it. I'm going to keep it with the 68 over 378, get the decimal limit. Negative 0.1011 t. Now we'll apply natural log on both sides because that allows that to go away. So I have the natural log of 68 over 378 equals negative 0.1011 t. Let's divide by that negative 0.101. So that and that cancels out. Negative 0.10. And we have just t here. So t is approximately, when you do all that calculation, do this number, do the log, natural log of it, and divide it by negative 0.1011, you get approximately 16,967, which is very close to 17. So this is approximately 17 minutes to get to 140 degrees. Okay. So let's revolve. Oh, and I need to actually put the formula since that's an interest problem. Okay. So now you know how to use Newton's law of cooling, which involves using natural logs, and also figure out the separate parts of the problem with the initial amount and then the amount at a certain time. Very similar to the other problems we've done. Let's do one more of these now as a practice. So take a moment to pause the video and try to do this yourself, and come back on what we're working on. Okay, welcome back. And so using the same information type of thing from the last one, we have the time and the temperature. Temperature at a certain time, and the C is the room temperature, and TO is the initial temperature. So we have initial temperature of 500. Okay, the room temperature is 72, and we have 5 minutes and 380. 5 at the time of 580, the temperature is 5 minutes, the temperature is 380 degrees. That's enough information to help us make the formula. So for A, I'm going to do that T equals C plus TO minus C times E raised to the power of KT. And with the information we have, we now say that the room temperature is 72 plus 500 minus 72 E raised to the KT. So 72 plus 428 e to the kt. Okay, now let's find the k. And we're going to use this one to find the k. So that's the temperature is 380 when the time is 5 minutes. 72 plus 428 e to the 5k. So we subtract 72, and that gives us 308. Careful of that 80 and 308. You can do it. 428 e to the 5k. We're going to divide by the 428, and that gives us 0.7196 is equal to e to the 5k. Now we're going to do natural log on both sides. Okay, and that gives us natural log of 0.7196. And also, of course, is approximation once we divided and use the natural log in it. It's approximately 5k divided by 5. So k is approximately, once we calculate that, negative 0.0658. So the decreasing rate is about 6.5%. If I would bring the decimal over twice, then and negative means it's going down. But now let's put that back into the actual formula here. T, the temperature at a certain time, is equal to 72 plus 428 E raised to the power of negative 0.0658 T. That's time for that temperature. Okay, so that's A. Okay, now let's look at B. So 20 minutes. There you go. What we just did is we just found the model. Now for B, we want to see what is it after 20 minutes. So that means we'll use this formula, but we'll put 20 in their place for time. T is equal to 72. Make it a clear 7. 72 plus 428E, negative 0.0658, and then the number 20. And then you calculate that out using the calculator, doing, of course, the exponent first, then e raised to that power, then multiplying it, then adding to it. Looks like 1, 2, use e, 3, multiply here, and then 4, add down there. You get it. And when you do that, you get that the temperature is approximately 187 degrees, and I'll put at 20 minutes. Not quite cool enough to eat, probably. That 140 from the last one probably was a little bit still hot, but edible. And actually probably very good. This one might be a little too hot. So that's doing B. So now we have at 20 minutes that's gone down from 500 to 187 degrees. Okay, and the last thing is, when will it become 100 degrees? So let's do that. We're going to use this other side, the right side, for part C. And we're going to use the same formula. T equals 72 plus 428E negative 0.0658 T. This temperature is what we want. We want, when is it 100 degrees? Actually, each of these can have degrees on them. But for calculation purposes, it doesn't affect anything for us. Raised to the negative 0.065. Is that right? 0.65 is good. T. So we're going to solve for T. Everything else is filled in there. So all we have to do is the calculations. So first it's subtract the 72. And we have 28 equals 428E negative 0.0658 T. And then we'll divide by that 428 here. And that gives us a decimal of 0.0654 equals E raised to the power of negative 0.0658 this part down in the main part of the fraction. And to do that, we use natural log here, because natural log allows that to cancel and the exponent to become part of the regular part of the problem, or regular area where you calculate things. 0.0654 negative 0.0658. Do I have these numbers right? Yeah, I guess I do. It comes out to a, it works out very well there. T, so we're going to divide by this one because we want to isolate that T, negative 0.0658. That means that T is approximately, comes out to 41.2. So that means it's about 41 minutes later. Temperature reaches 100, let it that way. Temp reaches 100 degrees about 41 minutes later. Definitely don't want your final answer like 4 decimal places for something. This is a practical thing where you would say, somebody comes up saying, hey, is the pizza ready to eat? Well, it's been 40 minutes, almost been a little more than 40 minutes. He's down to about 100 degrees. You go ahead, you can eat it. Unless that's too much for some people. Okay. And that means the 41 is the answer here. 187 is it here. The entire formula was this one. Same thing back on the last problem, showing that it was 17 minutes you were supposed to get. It was 210 degrees we were supposed to get. And this was the formula of the K in it. Okay. So now you have seen how to use Newton's law of cooling, and also simply modeling situations too, with population in particular, using a constant, finding a constant, putting an initial amount, and a time and amount, or time and temperature given to you for the purpose of helping to find a constant. Thank you for watching and listening. I hope that this helps.